I will be presenting our work, GRIT, GAN Residuals for Paired Image-to-Image Translation. Image-to-image translation is the problem of learning a mapping between images from source domain A to a target domain B. The source domain could be anything like edge maps, semantic maps, pose, etc. In our work, we look at paired data for syllabi mask HQ dataset, where we learn the mapping from semantic maps to real faces. We also look at edges to handbags, where we go from edge outlines of handbags to full handbags. Current image-to-image translation methods lack realism compared to unconditional GANs. We show on the left samples from style GAN at 1024 x 1024 resolution. On the right, we show image-to-image translation output from GAN at 256 x 256 resolution. Even at a lower resolution, image-to-image translation shows more noticeable artifacts compared to unconditional GAN. This is despite the fact that it has more inputs and better supervision during training. We investigate why this occurs and analyze the losses that are commonly used to train such models. We show here the effect of optimizing different objectives for image-to-image translation. Optimizing an L1 reconstruction alone leads to very blurry outputs, while using a VGT-based perceptual loss achieves much better results. The output is not sharp and contains clear grid artifacts. Adding an adversarial loss brings the output closer to the distribution of real images, but in many cases, artifacts can be spotted, examples around the hair, teeth, and eyes. We hypothesize that directly optimizing a reconstruction loss on the output ignores a type of multimodality in image synthesis, which leads to visible artifacts. To motivate our hypothesis further, this figure shows how GANs improve realism by simulating fine details found in real images, like local variations or noise patterns found in the texture of real material. There are infinite realizations of such noise patterns that add realism to the output. Example, skin freckles, pores and wrinkles, and linings of hair strands. However, applying a reconstruction loss in traditional image-to-image translation frameworks penalizes all these local variations and promotes a unimodal solution where the generated image matches the ground truth down to the pixel level. This leads to smooth outputs and other noticeable artifacts that do not show in the unconditional GAN setup where no reconstruction loss is applied. Through our approach grid, we address this problem and propose a modified architecture and training objective that relaxes the role of reconstruction losses to act as regularizers instead of doing all the heavy lifting, which is common in current image-to-image translation frameworks. As can be seen, we have an input image and style encoded latent, which is passed to a generator. The generator then generates the images conditioned on these. We apply reconstruction loss to one part of the output from the generator. Our formulation decouples the optimization of adversarial and reconstruction losses. This enables our network to hallucinate local variations to add realism to the output while avoiding being penalized by reconstruction losses. As discussed earlier, the reconstruction loss is applied to one part of the output, with the other part getting added to it and passed through the discriminator. This decoupling allows us to have good reconstruction, but at the same time allow local variations, as the GAN residual component does not have a direct reconstruction-based supervision and can increase realism based on the adversarial law. Here we show quantitative results on commonly used metrics for image-to-image translation, which include L1, PSNR, SSIM, LPIPS, and FID. We show these results on the Celebi Mask HQ dataset. As can be seen, Grid shows better performance across all metrics. Next, we also compare with other approaches qualitatively. We can see that Grid is able to have the most natural-looking reconstructions, which are also closer to the ground truth. We also show some qualitative results on the edges to handbags dataset, where we again show that Grid is able to generate the most faithful image-to-image translation from the edge maps to the real images. Here we show different outputs generated by our approach on multiple samples. The reconstruction column corresponds to the network output, which is supervised by the reconstruction loss, while the GAN residual is the output which is added to the reconstruction and passed to the discriminant. It can be seen that the GAN residual encodes more high-frequency information and local variations, while the reconstructed output is a more averaged image lacking details, but it captures the structure well. As talked in our motivation and approach, we allow grid to have spatial variation. This is done in our approach through introducing spatial noise and the decoupling of the reconstruction and adversarial objective. It can be seen that the highest deviation occurs in regions corresponding to hair around eyes, lips, and nose. These regions can be considered high-frequency locations as they usually contain multiple edges and have the most variation. We refer to the GAN residuals being high frequency by capturing local variations. We verify this by computing the frequency spectrum of the image. As can be seen, the reconstructed output contains more low-frequency information, while the GAN residual contains more high-frequency information. Adding both of them gives us a spectrum which is much closer to the ground truth. To summarize, we study the realism gap between unconditional GAN and paired image-to-image translation, highlighting the multimodal nature of the problem. We identify the problem of penalizing local variations in traditional image-to-image translation framework. We then propose GRID, which tackles the issue by decoupling the reconstruction and adversarial objective. Finally, we show quantitative and qualitative evidence showing the effectiveness of our approach. Thanks for listening.